Alright, in this video I'm going to prove Stokes Theorem. First I'm going to write down the equation, and then I will derive it. I just want to note, add this little note here in red, that Stokes Theorem is just really a three-dimensional version of Green's theorem. So remember, Green's theorem says that the line integral around a closed curve in the xy plane is equal to the double integral of some quantity over the region bounded by that curve. Well, Stokes' theorem is very similar. Okay, Stokes' theorem states that if you have a closed curve in space, okay, so this time we're in space, and you want to know the line integral around this closed curve, then that is going to be equal to the double integral of this quantity. This quantity here on the right says that the line integral around this curve in space is going to be equal to the flux of the curl through this surface. Okay, so I'm going to write down Green's theorem just so that you can compare. Okay, so I wrote the notation like this, indicating that sometimes this little curly d here is used to represent like the boundary. Okay, so this says that you have some line integral around some boundary, and it's equal to this quantity integrated over that region that's inside this boundary here. So you can see these two guys are very similar. If you remember, the reason we dot it with k here is so that this quantity actually ends up being, what was it, something like that. So that's why I wanted to show you guys Green's theorem written in terms of curl like this, because it's analogous to Stokes' theorem. Actually, Green's theorem is a special case of Stokes' theorem. It's the two-dimensional version of Stokes' theorem. Okay, so I'm going to prove this equation for you. Okay, like a lot of proofs, the trick to Green's theorem is to sort of simplify the left-hand side first and get it down as far as you can go, and then simplify the right-hand side, get it down as far as you can go, and show that the two guys are actually equal. Okay, so like I began to say, the trick to Green's theorem is when you simplify. Let's say we start with the left-hand side. You're going to want a parameterization for the curve. Okay, so this is usually how it's done. Okay, let the curve be defined by the parameterization. This is a position vector. Okay, and its components are functions of t. Okay, and then when you go to compute the right-hand side, you have to sort of simplify this situation a bit, sort of restrict it to a special case similar to what we did in Green's theorem, and say let S be Z is some function of x and y. So this parameterization here changes a little bit. Okay, we know that Z is a function of x and y, so we can rewrite this guy like this. Okay, where we substitute x as a function of t and y as a function of t in for Z here. Okay, so I don't want to spoil it for you, but you have a function which is a function of two variables which are themselves functions of another variable. So we're going to be using the chain rule a couple times in this proof. Okay, so when we did line integrals before, I showed you that dr is going to be equal to r prime dt. Okay, so we're going to do the left-hand side first. So I'm going to find out what dr is, and that's just going to be equal to the derivative of this position vector here times dt. So we have, and when we, like I said, we're going to have to use the chain rule. So when we find the derivative of this z component here with respect to t, what does the chain rule say? Okay, so quickly, we have z. z is a function of x and y, and then those two guys are functions of t. So if we want the total differential, or if we want the derivative of z with respect to t, then what do? Well, we go from here to here by doing partial z, partial x, and then from here to here we do the derivative of x with respect to t. Similarly on this side, and then we multiply these two together, and then we add both terms. Okay, so over here we're going to have the partial of z with respect to x. Okay, so I showed this in a previous video. Okay, so now let's say that this is a curve, or sorry, this is a curve that's in three-dimensional space, which means that our vector field is going to be in 3 dimensions. Okay, so we have a vector field, which is a function of x, y, and z, and let's say that its components are standard p, q, r, where each one of those guys are functions of x, y, and z. Okay, alright, so now if I go and compute this this dot product between f and dr, I'll have the integral of p times dx dt plus q times dy dt plus r times this z component here. Okay, and what would the bounds on this integral be? Well, our position vector is a function of t, so let t go from a to b. Okay, maybe when t is a, we're here, and then you go all the way around the curve, and then when you end up at the same point, that's when t equals b. Okay, so t goes from a to b. Now this next part is a little bit of a abusive notation. Okay, but this is a common way of proving Stokes theorem. It's in the James Stewart multivariable calculus textbooks. It's taught in university level multivariable calculus courses. Okay, so I don't really like treating this dt term here like it's a number that you can just multiply around, but anyway, they multiply this dt through by everything to end up with this. Okay, and then now they collect all the terms that have dx's and dy's in front of them to end up with this. And then what do we have here? Well, if I let this term over here equal some fancy looking p, and I let this term over here equal some fancy looking q, then what we have there is the integral of fancy p dx plus fancy q dy. And what's this? Well, this is one of the forms of Green's theorem. Okay, so this would be a integral around a curve, some curve c, I'll just c sub 1, some closed curve c sub 1. So in fact, that's what we have over here. Okay, and now all of our terms here are with respect to x and y, so they're in the domain of x and y, and that's this guy right down here, where x and y are inside this domain. That means that this curve right here is C1. Okay, so we've reduced this this line integral in three-dimensional space to a line integral around a curve in the xy plane. Okay, because we had we said that z was a function of x and y, and we were able to use that to our advantage. So what does Green's theorem state? Well, it states that if you have this form of Green's theorem, then this guy right here is going to equal the partial derivative of qx minus py dA. So a double integral of this quantity over the region bounded by C1. So that's what we're going to do here. We're going to use Green's theorem. So this guy right here is going to equal to the double integral over d of, so we need partial q, so that's this guy right here, with respect to x. So instead of writing fancy q, I'm going to put in q plus r zy. Okay, and then we subtract from that the partial of this term right here with respect to y, integrated with respect to x and y, like that. Okay, so we're not done yet. We're still working on the left-hand side. I said before that we were going to have to use the chain rule a couple times. Well, we're going to have to use it again. Okay, because remember we said that p, q, and r are all functions of x, y, and z. Okay, so let me just rewrite this for simplicity, and I'll include all the variables that these guys are functions of. Okay, so watch how fast I can write this. Wow. Okay, so this looks a lot more complicated, but I wrote it like this just to remind you that, basically I'm trying to show you that, let's say we want to find the partial of q with respect to x. We have some sort of branch structure that looks like this. Okay, so what are all our paths here that get us to x? Well, we have a partial q partial x. Okay. We don't do partial q partial x down this path, okay, because there's no x down there. But we do have to do partial q partial z, and then multiply that by dz dx, and then add everything together, right? So we have partial q dx. Oh, sorry, and should have wrote these guys here as partials, right? Because that's a function of x and y. So when we want to find the derivative of just this q term, we have to do something like this. So we're going to have to use the chain rule on all these guys here, and actually right here and right here we're going to have to use the chain rule and the product rule, right? Because we have these functions being multiplied by each other. So it gets a little hairy, and I just wanted to take the time to sort of show that so that it makes perfect sense to you. Okay, so just to remind you what we're doing, we're still working on the left-hand side of Stokes Theorem. We're trying to simplify it down as far as we can possibly go. I promise you the right-hand side's a lot easier and doesn't take nearly as long. Okay, so I'm going to drop all of the inclusions of these brackets with all the variables here and the partial symbols and stuff, just to simplify things and try to get everything onto one line. So here we go. We're going to do the double integral over the region. Okay, did I call that r up here? Okay, so that should be d. Sometimes I call the region r. That's why I wrote an r there. Look, see? Alright, so that's over the region d. These guys are over the region d. Sorry about that. Like I said, usually I put r as the region. D is good too. D stands for domain. That's how I think of it. Okay, so let's do this guy. So like I said, we take the partial derivative of this q term, and I wrote it up here, so I'll just write that down right quick. So we have, and then here's where we have to do the use the product rule. So when we find the, I'm going to use the chain rule on r. When I take the derivative of this guy and multiply it by that, I have to use the chain rule on r. So it's similar to what we have here, right? So that's this guy. So this right here is the derivative using the chain rule of that. And I'm using the product rule, so I find the derivative of this, multiplied by that, and then I add to that the derivative of this, multiplied by this guy. So in this case we just have r times, well, it's already the derivative with respect to y, and now I take the derivative with respect to x. Okay, so there's that term right here. Now I do the same thing on this side. So I'll just go through this really quickly, and hopefully it'll make sense to you. Okay, so now let's see if this simplifies at all. So before I told you that if you take the derivative of something in this order, so you take the derivative with respect to x, then take the derivative with respect to y, one of the properties of partial derivatives is that you can take the derivatives in any order. So that's called Clairaut's theorem. So you can see that if this is true, well, we have r z sub yx minus r z xy. Okay, so those terms are going to cancel. And then, since multiplication is commutative, we're going to have r sub z, z sub y, z sub x, and over here we're going to have r sub z, z sub y, z sub x. So this guy and this guy are going to cancel. So now let me write out the the simplified form of this. Okay, and then now let's collect the like terms here. Okay, so you can see that this guy right here has a z sub x, this guy here has a z sub x, and then this guy here has a z sub y, and this guy here has a z sub y. So let's collect those guys, and then this is it. This is it for the left-hand side. Okay, so that's the left-hand side. Now let's work on the right-hand side. So the right-hand side said, that line integral, which we said equals this, okay, is going to be equal to the flux across the surface that's bounded by C. So it's like this. So I talked to you guys about the gradients of a function and how the gradient vectors are perpendicular to the level curves, right? So we're going to use that here, okay? We said that z is a function of x and y, okay? So let there be some other function x that's equal to this, okay? And if I subtract these two guys, then that equals 0, right? Well, if I find the gradient of f, okay, then what that means is that, f is a function of x, y, and z. It's like this higher dimensional surface, okay, or like a hyper surface or something like that. So if I set this function equal to 0, then that means that this guy right here is going to be not a level curve, but a level surface of f when f is 0. Okay, so I'm not going to talk again about level curves and stuff like that. But this is, if you have a good understanding of level curves, and this is just like one step higher from level curves, it's a level surface. Okay, usually a level curve you would have. Okay, I really don't want to do this, but if you have, let's say you have some sphere like this, okay? If I want to find out what the level curves of this sphere are, then, I can set z equal to different numbers, and then I can plot the resulting circles here, right? Where, n is a bunch of different numbers. Okay, so sorry, Cn is just a bunch of different values of n, and then I subtract, I plug in values for z, and then I subtract both sides by z squared or whatever, and that's what this is over here. So you would end up having like a bunch of circles, like in the xy plane here, right? And those are level curves, and each of those level curves are when z takes on different values. Well, here we have f is a function of x, y, and z, and then when I let f take on a value, in this case 0, then that means that this guy right here is going to be a level surface, okay? And since we know that if I were to find the gradient of these guys here, then all of my gradient vectors would be perpendicular to all of these level curves. Okay, I showed you that before. I showed you some MATLAB code of that, I think. So anyway, so in this case, if I were to take the gradient of f when f is 0 like this, then I would have a vector field where the vectors are always perpendicular to this surface. Okay, so that means that if I wanted to compute this guy over here, I would have the curl dotted with this thing right here. And again, z is a function of x and y, so I let x and y be on that domain. So then, after I compute this dot product, it's no longer a surface integral. It's just I'll just leave it like that for now. But after I compute this dot product, it's not going to be over the surface anymore. It's going to be over this domain of x and y here. So we know that the curl of f is going to be equal to this determinant. So that's going to be equal to r sub y minus q sub z in the I hat direction, r sub x minus p sub z in the j direction, q sub x minus p sub y in the k direction. Okay, so now when I compute this dot product, Okay, it's going to be over the domain, because x and y are on this domain. And, well, what do I have here? Well, I multiplied this x component by this guy, this y component by that guy, and that z component by 1 here. So I'm sure you can already see that it's going to equal that, but I'll write it out just to show you. And there you have it. So we showed that this is the right hand side. Up here was the left hand side, and you can see that these two guys are very much equal, and that is the proof to Stokes Theorem. So thank you very much for watching. I know that took a long time. In the next video I'm going to do some examples. Thanks.